Hello and welcome, and in this video we're going to be talking about solving nonlinear systems. Now we've already talked about solving linear systems, which is when lines intersected one another, or with three variables, or when planes intersected one another, but they were all linear equations. Now when we cover nonlinear systems, okay, that just means that one or all of the equations in the system are not going to be linear, and we're going to be talking about how to solve them algebraically as well as graphically. So as we can see here, we have a quadratic equation. We have a quadratic equation and a linear equation. So this would be a nonlinear system. What we're actually finding is the point or points at which this line intersects this parabola. Now, I'm going to start by solving it algebraically. And me personally, I like to use substitution a lot when I am covering nonlinear systems. And I always look to see if I can solve for a variable fairly quickly. And in this particular problem, we actually already have a variable solved for. If I look in this first equation here, we actually already have y solved for. So this would be a prime candidate for substitution, because what I can do is I could take x squared plus 4x plus 8 and substitute it in for y in our linear equation. Now, remember, substitution and elimination are from the previous video, so if you don't know how to use those, make sure you go back and watch those. But if you're here, you should know how to use them. So I'm going to jump right in, and I'm going to go ahead and substitute this quantity in for y. So we get here, and now what's nice about this is we actually have an equation in only terms of x. So what I can do is I can distribute this -3, combine like terms, and then try to solve it. And since this is a quadratic and the x squared is not going to cancel out, we're going to have to either solve by factoring, quadratic formula, completing a square, one of those methods that we have already learned. So I'm going to go ahead and get this set up. So I went ahead and distributed combined like terms, and I'm left with -3x squared minus 9x. So 24s end up canceling. Since I'm left with this, all I can really do, well, I guess I could complete the square or use a quadratic formula, but I find it unnecessary because we can just go ahead and use the greatest common factor. I can factor out a -3x, and now I'm left with -3x times a quantity of x plus 3, which, remember, means that we can solve by factoring. So -3x is equal to 0 and x plus 3 is equal to 0, which means that x is equal to 0 and x is equal to -3. But remember, we're not done here. Solutions to a system are the points at which the graphs intersect. What I have here is only the x coordinates. So what I need to do is I need to substitute each of these x coordinates into one of these equations to find what the corresponding y coordinate is going to be. So I'm going to go ahead and plug 0 into this equation, solve for y, that will be a solution, and I'm also going to take the -3, plug that in, and that will also be another solution. So let's go ahead and do that. And there we have it. There are our two solutions. So we have a solution of 0, 8, and we also have a solution of -3, 5. So these will be the points at which the parabola and the line intersect one another. Now we can also graph it in our calculators and take a look at the graph to see if those intersections make sense. Now, you should already know how to use the intersection tool in your calculator, so I'm going to go ahead and open up this in a separate program. But let's take a look at the graph to verify our answers. So here's our solutions, -3, 5, and 0, 8. Now we can clearly see that it's two solutions graphically speaking because we see the line intersecting the parabola at two separate places. So that is one possibility. We can have two intersection points, which means we have two solutions. Now it is also possible for the line to intersect the parabola at only one spot, which is where it kind of barely goes along the edge of the parabola. That's actually sometimes referred to as a tangent line. We'll be covering that a little bit later, but it is possible to have one solution, and it is also possible to have no solution, and that would be when the line does not intersect the parabola at all. So if we're ever dealing with just one line and one parabola, those are your three options, either two solutions, one solution, or no solutions. Now, if you were solving algebraically, we did just see how to get two solutions solving algebraically. We had two different values for x. So that meant we were going to have two different values for y, or we would have 2 points. Now it is possible to get one solution. You would only have one value for x or one value for y. That would get us one solution. And the way to determine algebraically if there's no solution for a system is if your solutions actually contain imaginary numbers. Remember, our solutions that we see are only going to be real. So if you ever get imaginary solutions in a system, that means it is no solution, or no real solution at least. But that is this particular problem. Let's go ahead and take a look at another one. All right, so let's take a look at this new problem. So we have negative 3x squared plus 29x plus 2y minus 78 is equal to 0, and x minus 2y is equal to negative 3. So once again, we have a line and a parabola. So remember, I tend to use substitution, and if I'm looking at this system, I'm noticing that I can solve for x fairly quickly in the second equation. That would end up getting us x is equal to 2y minus 3. And what I can do with that now is I can use substitution and substitute that in for x everywhere I see an x, everywhere we see an x in the first equation. So I'm going to take this and substitute it in for x here. I'm also going to take it and substitute it in for x here. So we are going to get some fairly large numbers in the beginning. So make sure you have your calculator ready. So I'm going to go ahead and substitute that. Okay, and now we're going to have to go ahead and distribute and multiply, combine like terms. Just remember that 2y minus 3 quantity squared, you cannot distribute that power. Remember, that is multiplication, 2y minus 3 times 2y minus 3. So make sure that you do that. Okay, so I went ahead and multiplied that out and combined like terms, and I'm left here. Now, all these numbers are pretty big. However, what you might recognize is that everything does have a greatest common factor. Everything does, in fact, have a greatest common factor of 12. So what we can do to make this a little bit easier is we can divide each side through. I'm going to divide by negative 12. That way, my leading coefficient is positive, and this is going to leave us with an equation that is much easier to handle. And as we can see here, everything is a lot easier. Yes, this is y squared instead of x squared, but that should not prohibit us from factoring at all, because we can solve this by factoring, and in fact, it gets us y minus 4 and y minus 4, which you can think about as y minus 4 quantity squared. Now, since it is the same binomial happening twice, that actually means that there's only going to be one solution, and that solution is when y is equal to 4. And remember, we need both the x and the y coordinate because we're finding an ordered pair. We're finding the point at which these graphs intersect one another. So we have to substitute this in to solve for x. So I would personally substitute it in right in here because x is already solved for. So let's go ahead and do that. And there is our solution. We actually only have one solution, a single point, and that point would be the coordinate 5, 4. Now, if we were to take a look at the graph, we would actually see that it actually only intersects once. And here is the graph for this problem, and as we can see, it intersects the parabola only at one point, and that's the point 5, 4. So that is the example of a graph when you're only going to have one solution. Now, like I said before, we can get no solution, and that would be when the line does not intersect the parabola at all. And that's it for nonlinear systems. Now, there are more complex problems, which we might get to in later videos, because this was just a line intersecting a parabola. We could talk about parabolas intersecting one another. We can talk about a circle intersecting an ellipse. Those are all examples of quadratic systems, which are technically nonlinear. So we could see those as well. But that is it for nonlinear systems. I hope this video was helpful. If there's any questions, please feel free to let me know, and I look forward to seeing you all in the next video.